Yeah, I am a.
I talked to Larry Long.
Oh, you did? What he say?
You remember everything I told you. He also told me to ask you about steam engines or range engines.
Oh yeah, Inslee ran off a steam engine.
I didn't know that.
Not the whole plant. That was the rolling mill ran off a steam engine, and it was so neat. It'd be over there going.
This last years.
Oh, years. And they had the bearings in the engine were wood. They were wood bearings on that engine. So it was a
Y'all want to talk about curves?
Curve Master.
Yeah.
Yeah, we spent a lot of time over there. It was a place where the two categories of transistors are bipolar junction transistors or BJTs, and then there's only two of those. There's an NPN and a PNP. When we get into the field effect transistors, there's 6 different kinds of FETs. So they're a little more complicated. But the major difference is the BJT uses a small current to control a big current, and then the FET uses a voltage to control the current. And you'll find out what advantage FETs have over BJTs and what advantage. So there's room in the field for both types. And then we look at the construction, talked about doping, looked at the two symbols that we use. Everybody okay there? P and P, which we would say pointing in, and NPN is not pointing in. So primarily an NPN is biased with a positive supply, and a PNP is biased with a negative supply. It don't mean you won't run into them, because you can swap things around. It's really cool. Which means I can hook the collector toward ground, and we could forward bias it, but you won't see that much. And we talked about forward bias and reverse bias. So the base emitter is forward bias, and the base collector is reverse bias, right? Everybody okay? And that's the way we bias a transistor to turn it on. And we also know to turn it on, we got to get up to around 7/10 of a volt on the base. So anything below 7/10 of a volt, the transistor would be cut off. And when it's cut off, we have no current flow between the collector and the emitter, or current that we can measure, right? You'll understand. Yeah, it's just, you got to understand there is a path for the current to get through. So it's not like a switch, because a switch, when you open a switch, there is no path. You're breaking the circuit. Here we have a path. Now it's extremely high resistance, but there's still current flow through that. And then when we put 7/10 of a volt, over 7/10, it will start cutting on, and then it goes into what we call the active region. Well, the active region, it acts like a rheostat, and that's what does a rheostat do? So what's the difference between the function of a rheostat in the circuit and the function of a potentiometer in the circuit? They're both what we call variable resistors, but if they did the same thing, then we wouldn't have two types, right? So what's the difference? What does a rheostat do, and what does a potentiometer do? Well, we use potentiometers for resistance. We use resistors for resistance. So what's the function of a rheostat? Well, rheostat controls a current. A potentiometer controls a voltage. So normally what we do is we use a potentiometer as a variable voltage divider. So we can hook it up across the source, and then we can adjust this thing we call the wiper and get any voltage we want to between what's at the top of the pod and what's at the bottom of the pod. So what that means is I can come over here on a potentiometer, and if I wire it correctly, I can come over here like this, and then I can hook it across the source. I'm going to put it DC, but it could just as well be AC, and then make this common. And then we come over and we take this thing called a wiper, and then I'll come over here and hook this to a meter. And if I have 10 volts up here, then I can get any voltage across that from that meter from 0 volts up to 10 volts. just by adjusting the wiper. And we're going to have to use them. We're going to have to use them. Because it's just like when we did the diode, we had to start below 0.7 of a volt. Well, the problem is our power supply puts out about 1.5 volts. So what did y'all do? Well, you used a potentiometer and you put 5 volts over here, so you could adjust this thing anywhere from what? From 5 volts down to what? 0. Well, if I come over here and have a rheostat, and it's a 10K rheostat, then I can adjust this resistance. So if this is a 10K pot, it'll always be a 10K pot between those two leads. Always a 10K pot. So the resistance between pin 1 and pin 3 don't change. Y'all understand that? Unless I hook something in parallel. Over here, if this is a 10K pot, if I come over and start adjusting this, this will adjust anywhere from 10K down to 0 ohms or 0K. So what am I doing here? Well, when I start off with 10K, I would have a certain amount of current. When I got to 0, I'd have a short circuit. So a rheostat controls a current. A potentiometer controls a what? A voltage. And we can make a potentiometer act just like a rheostat if we come over here and we connect the wiper to one side. And so you're going to run into a lot of pots wired as a rheostat. Because here's something that I've got that can serve two functions. They cost about the same price per K, so you can't hardly find rheostats anymore. Because why? Because a pot can do the same thing if you wire it correctly. So if I wire a pot like that, it acts like a rheostat. If I wire it like this, it acts like a potentiometer. It is a potentiometer. So if I'm going to do this, I got to be real careful, because I could create a short circuit with a rheostat. But if I come over here and put a fixed resistor right there, and then I put my rheostat, what's the rheostat doing? Well, it's changing the current flow. So if this is a 1K, and this is a 1K, if I adjust, and this is 10 volts, well, if I adjust this down to 0, then this guy's going to be dropping 0 volts. That guy right there is going to be dropping 10 volts. But I'm doing it by changing the current flow, right? You understand? If I drop this down to 0K, then the top resistor is going to drop all the voltage, and the pot is not going to drop any. But how is the rheostat changing the voltage? Well, it's changing it by changing the current flow in the circuit, right? You understand that? Does that make? So the pot across the pot, the current flow don't change. It's always the same. Well, what we're doing with our transistor is we're acting like a rheostat. So what I have to do, if I run it like this, we have to put a resistor in series with it. Because if I adjust it all the way down to 0, my dang something's going to burn up because I have a short circuit. So when we run a transistor like this, we'll always have this resistor we call a collector resistor. And so what we're doing is we're varying the voltage drop across this guy, and so when the voltage drop across here goes down, the voltage drop across here is going up, because Kirchhoff's law says the sums of the voltage drop. Now what's causing the voltage drop across that to go up? Because the resistance on the resistors the transistor's going down, the current flow in the circuit's going up, which is causing that top resistor to drop more voltage, right? You understand? But we're doing that by controlling the current. And that's why a transistor is a current valve. But in electronics, it's the equivalent of a rheostat, but a rheostat's got a knob on it. A transistor don't have a knob, because we're controlling that resistance of that transistor with a base current. And we can control it precisely. I mean, we can do all the calculations in the math. It's really neat. But as soon as I hit about 0.7 of a volt right here, the transistor turns on and it starts acting like a rheostat. Well, eventually, if I'm going to get that rheostat, what's going to happen when I adjust this to 0 ohms? Well, what's going to happen now is this guy right here is going to drop all the voltage. And here we say the transistor is what? Saturated. So when it acts like an open switch, we say it's what? It's in cutoff. When it acts like a closed switch, we say it's saturated. And if it's in between saturated and it's in between cutoff, and it acts like a rheostat, we say it's in the active region. So your amplifiers operate in the active region, where I can bring an input signal into the base that's varying, and my output varies, but it has a current gain, right? You understand that? And where's the current gain coming from? It's not coming, the current gain is coming from the power supply. All the rheostat, all the pod is doing is just changing the current flow from the power supply. So transistors don't create current. Transistors don't create power. What do? They control it. They control it. And I think I told you to go out there and disconnect your battery and turn your radio on. What will it do? Nothing. Why? There's no power. So everything in your radio controls power. The power from your electrical system in your car, right? That's already there. So the three regions we can operate this thing in is we can operate it in cutoff, and we can operate it in saturation, or we can operate it in the active region. And if we want to use it as a switch, which is what we're going to cover first, is we're going to switch it between saturation and cutoff. So we'll put enough base current in it to cause its resistance to go to minimum. It's not going to go to zero because it's not a switch, right? So a transistor will drop a voltage when it's saturated, but it's usually going to be less than 1 volt. And then when you cut it off, your transistor is going to drop the applied voltage. We can't measure it. There's so much leakage current through that thing, we can't measure it, as long as we operate it below breakover. Are we okay? Yes or no? Collector current, NPN transistor, we went through, watched a real neat video. That was a pretty good video, right? Then we talked about the base current, which is the highest current in the transistor? Emitter current, right. Followed by the collector current, followed by the, well, it's not even followed by the base. The base is way down there. The base is not even near these. But what we're going to do for our calculation is we're going to assume the collector current and the emitter current are the same, because they're such a little different, but they are not the same. And like I said, if you see in a test it says the collector current and the emitter current are equal, what are you going to answer? False. If I say they're approximately equal, you're going to say what? True. And here's the three regions. And we talked about beta. What's the beta? This is probably one of the most important things that we'll use when we try to figure things out. And you'll see when we get into amplifiers, we're going to try not to use this. But when we do saturated switches, we got to use beta. So what is beta? It's what? Base. It's the ratio between the collector current and the base current. So it tells us our gain. It tells us our current gain. Now remember, a transistor is a current valve. It don't control a voltage. It controls a current. Now we can run that current through a resistor and make it appear to be controlling the voltage, but the transistor is not controlling the voltage. It's controlling the amount of current. And then we use a resistor up there in the collector, right? You understand? And when the transistor's current flow changes, then the voltage drop across the transistor changes. Y'all understand that? But a transistor is a current valve. So if you see that, if you see a transistor controls the voltage, what are you going to say? Is that true or false? Transistor controls the voltage. Is that true or false? It is false, because it controls the current. If I want to change a voltage, then I'm going to have to put that current through a fixed resistor, right? You understand? So don't get confused with that, because the transistor is not controlling the voltage. The transistor is controlling the current, and the current flow through that resistor is what's changing the voltage. But in your data sheets, it's going to be called H of FE, which is the hybrid forward transfer ratio with the emitter common. So we have H of FC, we have H of FC, and we have H of FB that are available. H of FB and H of FC is not usually given because if we need them, we can calculate them from H of FE. And this is the formulas for beta. So if I know beta, I can calculate the collector current for that beta. I can calculate the base current that's required to get that base current. Are we okay? Everybody okay? And these formulas should be on your phone. And DC alpha, this is going to come into play when we start dealing with what we call a common collector amplifier. And this is not given in the data sheet. And I don't even know if the book talks about the alpha of the transistor, but we can calculate the alpha of the transistor will always be less than 1. But it's going to be close. It's going to be like 90%, right? It's the collector current over the emitter current. Then we talked about the different voltages. This is very important, guys, because this is what you're going to have to solve for. You're going to have to solve for VB, you're going to solve for VE, VC, VCE, and these different voltages. And if you don't know what they mean, then that's going to give you problems. So AK on these, and these are all relative to circuit common. So VB, these are all relative to circuit common. This is in the textbook. I just read it. I don't know what page it's on. The chapter for bipolar transistors, by the way, is really good in the book. So here's where we would measure them. So it just shows you that. But remember, these are all relative to what? Yeah, these are all relative to circuit common. Now later on, we're going to put a resistor in here, by the way. So right now, VE looks like it's going to be equal to 0, which it is, right? But later on, we're going to put a resistor in there, and we'll show you why. Then we have these voltages, VBE, VCE, VCB, the most important being VCE. And why this is the most important, because this tells us the region that the transistor is operating in. Which means this tells us if the transistor is saturated, it tells us if the transistor is cut off, and it tells us if the transistor is in the active region. Now what this guy here is telling us is this is telling us where we make our measurements. So VBE would be a measurement between the base and the emitter. And which one is meter common? Not circuit common, meter common. Y'all got to understand the difference, right? So this black lead, this is not circuit common. This is meter common. So this is what your meter makes measurements relative to. And where can we put this in a circuit? Anywhere we want to, right? You understand that? Because this is not circuit common. This is meter common. We can't move the common of a circuit around in the circuit. But we can move this around because this is not circuit common. This is meter common. So what these are telling us, VBE means we're going to measure this. We're going to put the emitter is going to be common. So the one on the right, this is your common right here, meter common. So on an NPN transistor, this would be positive. On a PNP transistor, this would be negative, right? You understand that? Because the base has to be negative in respect to the emitter. Voltage collector to emitter, this tells us the region. If it's dropping less than a volt, we consider it to be saturated. If it's dropping the supply voltage, VCC, we say it's cut off. If it's somewhere in between, we say it's active. You understand that? So being able to identify the region, this is the guy right here. I just take my meter, I put it across the collector to emitter, I know exactly what's going on. And this tells you a lot. Because if it's supposed to be an active region and I measure the dang thing and it measures saturated, then you're going to be able to zero in on the cause of that right off the bat. Very fast. Collector to base, this guy should be reverse biased. So it's a NPN, so that means if we go between the base and the collector on an NPN, it's going to measure positive. So you're going to have a positive on the collector, right? Because the collector base has to be reverse biased. Are we okay? And this is the way the measurements will be made. And then the supply voltages. So the supply voltages are going to be called VCC. It depends on what they're connected to. VBB and VEE. This is the power. This is not the common. This is what we actually. So this would be this guy right here would be what? This guy right here would be VCC. In fact, it's marked. This guy right here would be what? VBB. And right now it's hard for us to do a VEE. Are we okay? And we looked at the model, and this is what we got to understand. If we can solve these like two different circuits, you're going to find is DC. DC, that's all it is. And we looked at this. We saw for this, right? Looked at our characteristic curve. The one in the book's not exactly right. So down here, this is voltage collector to emitter. So what is this right here? If that's 0 volts, what does that mean? Means it's what? Saturated. If this equals to VCC, so VCC goes this way. If it means it's equal to VCE, I'm sorry, it's equal to VCC. If VEE is equal to VCC, and this right here is if VCE, so this is VCE. So if VCE is equal to 0, the transistor is saturated. Either that is turned off, right? You understand? So we can't say, this is if the circuit is turned on. If you measure 0 across the transistor's collector to emitter, it's saturated, or less than a volt, right? If you measure VCC across here, then it's what? It's cut off. Now, if you keep increasing VCC, eventually it's going to do what? If it's cut off, and there's a path through there, well, eventually you're going to hit a voltage we refer to as the breakover voltage. Is that good or is that bad? It's bad. So the only time it's good is on a zener. And still, you've got to protect your zener, right? You understand? You've got to protect that zener. If you break over a regular diode, if you break over a rectifier diode or a switching diode, if you break it over in the reverse, we call it peak inverse voltage, right? If you break it over, you're going to mess up that diode. If you break over a transistor on any of its junctions, you're going to mess it up. This is not even a junction. So I've got 15 volts across that dang thing, and all of a sudden I get a current spike through it. 15 volts, 15 amps. You know, that's 100 watts. Well, what's going to happen to the transistor? It's going to go just like that. Transistor's going to pop. And these guys, by the way, these guys will pop on you. If you screw up, they will pop on you. Now, the problem is when a transistor goes bad, it can go bad 3 different ways. We can open it. We can short it. It will short. A transistor will short. All solid state devices will short. Or it'll be what we call leaky, which means it don't work. It acts like a resistor. It don't act like a semiconductor anymore. So this is one of the major things we're going to look at. Is called voltage collector to emitter. It's called voltage collect. It's called this V sub CEO. I bet nobody here knows what that stands for. What it stands for is the voltage collector to emitter with the base open. Well, if the base is open, the dang transistor is cut off because there's no way in the world it's going to get any base current, right? You understand that? So the transistor's cut off. So, and if you exceed that breakover voltage, what's going to happen? The transistor is going to be destroyed. And something else in your circuit might be destroyed. Because if the transistor shorts, that's what usually happens. These solid state devices, when these guys short, it's usually cascades, which means this guy will short, it'll pop something else, and so we get into it'll burn resistors up, right? You understand? Because that resistor was designed not to handle a short circuit. So you short the transistor, and you got that collector resistor up there, you know, 1/8 of a watt, 1/4 watt, and all of a sudden it's doing 5 watts. What's it going to do? It's going to burn up, which could cause all kinds of things to happen. So this is the problem we have with solid state. When one thing fails, it usually causes what? Multiple things to fail. So what we'd have to do is know the cutoff voltage, which might be somewhere in here. So the cutoff voltage is going to be below the breakover voltage. And then the saturation, where it saturates at. And then we can come over here and draw a line between that. And what we want to do, if we're going to operate it in the active region, we would try to bias it in the center. And then what I can do is I can come over here and apply an AC current to the thing. And then we can come over here and we can figure out exactly what's going to happen to this guy down here. It's really, really neat. But the problem is, guys, is they don't give collector curves anymore. Unfortunately. But using the beta, you could generate them. It's just a true collector curve. This is going to have a slant. Transistor switches, single power supply bias. So when we back here, the way we first teach transistors, we teach it with two sources. But in real life, you're not going to run into this, right? Y'all understand that? So how would we bias this with a single power source? Well, one thing, we've got to have a collector power supply. We've got to have a collector power supply. Because this is the guy that's providing 99% of the power. Now, of course, when we do this, it's going to be providing 100%, right? And then I could come over here and I could hook up my transistor like this. And let's do it like this right now. And then up here, let's say this is 15 volts. Now I've got to get a positive voltage to the base. So how can I get a positive voltage to the base without using another power supply? I can come over and take a wire right here, and I can come over and I can come it down, and then I put a base resistor right here. And this is called base bias. So we got 3 ways we can bias a transistor. We can base bias it. What would you think the other 2 would be? We got 3 leads, guys. Emitter bias, and we got collector bias. So base bias is used to saturate a switch. So this is the first one that we use. Now this guy here is going to be a big resistor. So let's say I want to saturate it, 15 volts. Then what I want to do, let's say this is a 10K resistor. By the way, generically, what we're going to do, generically right now, is we're going to call this resistor RC. Now in real life, it's going to be a R52 or an R32 or something like that, right? But just for generics, and also in our math, because in a circuit, I don't know if it's R15, I don't know if it's R32, it might be R1, I don't know that. But if in my math, if I call it RC, then you know which resistor it is, no matter what it is in a circuit, right? Does that make sense? Okay, so what would it be when it saturates? Well, how do I know when it saturates? Well, how would we do that? So what I'm trying to do is I'm trying to come up with my collector current. So what would the collector current be, guys, when it's saturated? Anybody got any guesses? So when the transistor's saturated, it acts like a closed switch. If the transistor acts like a closed switch, how much voltage is going to be dropped across RC? How much, Courtney? Oh my goodness. No, it acts like a closed switch. So what I'm going to do is I'm going to come up here and put 15 volts. I'm going to come down here and put a straight piece of wire because that's the way I'm going to draw the switch right there. I'm going to draw the switch. I'm going to put a straight piece of wire. How much voltage is that resistor dropping? 15 volts. So when the transistor's saturated, we're going to assume that the resistor is dropping 15 volts. Sorry, Courtney, you okay? Yeah. Okay. So it acts like a closed switch. So how much current would that be? So I would come up here and I'd say VRC would be equal to what? 15 volts divided by 10K. What's that going to be? Good. 1.5 milliwatts. What? Milliamps. Okay, guys. So what do I need to know now? That wasn't hard. What do I need to know now if I'm going to go ahead and figure this thing out? So what controls that 1.5 milliamps? Close. But I can't do VRB yet. What controls the 1.5 milliamps? How did I get the 1.5 milliamps? Huh? Not base voltage. This guy uses a current to control current. So what do I need to know? I can't do the base resistor unless I know the base what? Base current. Well, I know the base resistor. What is the base resistor going to drop when the transistor turns on? What voltage is going to be dropped across the base resistor when the transistor turns on? No. What's going to be dropped across the base resistor if the transistor turns on? What's that? What's going to be dropped across the base resistor when the I've got to drop, Kirchhoff's law says I've got to drop all this voltage. I got to drop all this voltage. So I've got to drop all this voltage from here down to here. So how much does this guy drop? How much does the base to emitter junction drop? It's a diode. How much does it drop? How much does the diode drop? How much is the silicon? 17. Okay, so this diode right here, voltage, base to emitter is going to equal to 7/10 of a volt. Okay, so if it equals 7/10 of a volt, Kirchhoff's law says I've got to drop the entire voltage down this path right here. Because this is a series string right here. How much is dropped across the base resistor? 14.3. Good. So V, we're going to call this RB right now. RB is going to be equal to 14.3. So I know RB is dropping 14.4B. So what size resistor am I going to use over there? What do I need to know, guys? R is equal to Ohm's law says R is equal to V over I. Okay, so I know the V, I don't know the I. Okay, so how do I know, what do I need to know to find the base current? The beta. Okay, so we need to know the beta of the transistor. So what beta do y'all want to use? Well, we'll look, what we're going to do later on is we're going to look the beta up on the data sheet to calculate this resistance. But right now, just for practice, we can choose any beta you want. What do you want? 13. That's a strange beta, but that's okay. Now, normally your beta is going to be up in above 50. Well, let's use 50. This is your big high current transistors. The beta is low. Even the high current transistors have a pretty good beta. So let's use 30. So I got a beta of 30. Now I know beta. What's beta equal to? It's equal to IC over IB. So what I'm going to do is I'm going to solve for IB. So what's IB equal to? Well, IB is going to be equal to what? IC divided by beta. So IB would be equal to, what's our IC? 1.5 milli divided by the beta that I gave y'all was 30. What's that? 15 micrograms? Well, 50? Yeah, I'm sorry. Micrograms. Okay, guys, what size resistor would I use? And we're going to calculate this perfect, and we'll talk about what we're going to do later on. In fact, we'll go ahead and talk about it now. So what size resistor would I use? $14.3 divided by what? R is equal to V over I. 13.3 divided by 270K. I think that's a standard resistor. Now, why did you go down? So that's what we would do. We would always round down. Why would we round down? Because this is the exact size resistor to cause it to saturate. Well, if we put more current in, that then requires to saturate. So you can't saturate it more than saturation, right? You understand? So what we would do is we'd always round this down. Always. And then we check the tolerance, but we'll talk about that. So y'all calculated y'all first. Now, how would we control this? Well, I could come over here now. Oh, sorry, I'm hitting my power cord. So right now I could come over here and take me a little old tiny push button. A little old tiny push button, because this only won't have to conduct 50 microamps, right? A little more. And I would come over and take my push button. And I would take this side and hook it to common. So when I press the button, the transistor would cut off. Why would it cut off? Because we're bringing the base to 0. And then this resistor right here is going to drop 15 volts. It's not going to drop 14.3 anymore. It's going to drop 50 volts. But if I put the base at 0, then it's going to do what? It's going to cut off. As soon as I let go of the switch, it's going to do what? It's going to saturate. Now you got to imagine this resistor right here could be anything. It could be a relay, right? Contact. But what we're doing is we got 50 microamps of flow through that little switch. We got 1.5 milliamps of flow over here, which is pretty neat. So this allows us to control. This could be a digital logic gate. A digital logic gate can source 400 microamps and it can sink 16. It can provide a high of up to 400 microamps and it can provide a low up to 16 milliamps. So this could definitely be drawn by a digital logic. Microprocessor would have no problem with it, turning this thing on and off. You understand that? And we'll look at it later on and we'll calculate that. What they talked about on the slide was doing this. Now, if this had a beta of 30, and this would have a beta of 30, what would be my total beta? What do you think, Frank? Huh? What would be the total beta? So if I take a transistor that's got a beta of 30, and I feed it into a transistor that's got a beta of 30, what would be my total beta? Beta is a gain. So let's say I have $1, and my boss says, okay, I'm going to multiply your pay by 30. Now I got $30. And then he says, okay, I'm going to multiply your pay by 30 again. So beta is a multiplier, right? Y'all understand that? IC is equal to IB times beta. So what would be the total gain? 900. So just putting two little transistors together, I get 900 million, a gain of 900. So that means if I put 50 microamps over here, take 50 microamps and multiply it by 900. Pretty good current gain, right? So we do this a lot, especially if you're going to use something that can't provide a lot of current. By the way, this is called a Darlington pair. This arrangement has been around so long, you can buy these guys. You can buy them. It's got, all you need is 3 leads. It looks like a transistor because all you need is this lead, and that lead. And the transistors are hooked together inside the block. And it looks like a transistor. Looks just like a transistor. But they're called Darlington pairs. You're going to look at these suckers. They're going to have betas of 1,000, 10. I've seen them with a beta of 10,000. Very easy to get a beta of 10,000, right? So if this has got a beta of 100 and that's got a beta of 100, that's a lot of beta, right? You understand that? So Darlington pairs. So this is very popular, especially in saturated switches. So we get extremely high betas just by doing what? And this is what the guy was showing y'all on the video. I don't know if you remember. He took the base out. We usually don't use this for stereo amplifiers, and we'll look at later on why. But we use this a lot of times for saturated switches, especially if I'm going to let a microprocessor drive something. A microprocessor can't source a lot of current, but this it don't need to source a bunch of current, right? What's this called? Can y'all read it? Darlington pair. It's called a pair. You run them in pairs. We'll talk about some more advantages of that. So this is what we do. This is the way we design them. First of all, let's look at the data sheet. So y'all will log into Blackboard. And the transistor we're predominantly going to use is a 2N3904. So most of your transistors, by the way, and it's not always true, it's just like diodes. So diodes start with 1N. And what that means is it's got one junction, right? You understand? A bipolar transistor has 2 junctions. So its generic numbers start with 2N. And then it'll have a number out beside it that's basically assigned when the device is registered to JDEC. So we're going to look at a 2N3906. Two N because we're dealing with transistors, 2 junctions now, right? Y'all understand that? Now we got some TIP41s and TIP42s. And I can find Zener diodes that have different numbers on them, but those are what we call JEDEC registered devices, which means these are open technology devices. So when we go on our website, we can go to data sheets, and then we're going to go to the data sheet for the 2N3904, which is an NPN transistor, 2N3904. And these are the different packages. And these are called TO for transistor outline. These are JEDEC. We talked about JEDEC, right? What's JEDEC? Joint Electronic Device Engineering Council. These people allow you to register open technology packages. And what that means, anybody can use this package. So if you see this package, does it mean it's a transistor? No. It could be an integrated circuit. If I can fit an integrated circuit, so a voltage regulator would have three things. We need unregulated in, we need regulated out, and we need a common. So just because, and we got one in a TO92 case. So ours in these little TO92 cases, these are plastic cases. These are small outline transistors. These are surface mount, and this is just a small outline right here. Surface mount, these are what we call through the hole devices. So that means when you solder them on a printed circuit board, it actually goes through the board. A surface mount device only solders on one side. Then we have the absolute absolute maximum rating table. What's the absolute maximum rating table? Same thing on diodes. What is absolute maximum? What's it? It don't mean if you stay with this range, it don't mean it's going to operate. It just means it won't be damaged. What we'll do is we'll get down to these electrical characteristics. So here's our breakover voltages. So voltage collector to emitter with the base open. This guy can handle 40 volts. If you get it above 40 volts, it breaks over, you got problems, right? Everybody okay? Maximum current, we can conduct in the thing. IC, collector current, continuous is what? 200 milliamps. So when we saturate this sucker, this is all we can get, 200 milliamps. That would be maximum. If we tried to do more than 200 milliamps, then what's going to happen? We're going to burn it up, what we're looking for down here is beta, H sub FE. And we'll look at these other things. Okay, we'll look at a couple of them here. Here's H sub FE, and this is the problem we have with H sub FE. What's the minimum it could be? Everybody shows up on Blackboard? What's the minimum it could be? What's the minimum beta could be? What's the minimum? So notice we got two columns. We got minimum and we got maximum. What's the minimum beta could be? No, we're not looking. Beta is not a milliamp. Beta is a number. It's a multiplier. Beta has no unit. So beta has no unit. It's a multiplier. It's just like I'm going to say, I'm going to triple your salary. You say, well, that's great. I'm going to get a $3 an hour raise. And I'm paying you $10. Well, I'd love for you to come to work for me. Because I'd say, I'm going to triple your raise, and you think you're going to get a $13 an hour raise. You're going to 13 instead of what? 30. So, but that, when I say triple your salary, that unit that's a multiplier. That has no unit. Gain has no unit. It's a multiplier. It's a multiplier or it's a divider. I mean, that's all it is to it, right? So the minimum it could be would be what? 30. The maximum it could be would be what? 300. So what am I going to use when I saturate this thing? Huh? Why? That's exactly right. We will use 30. Why? Huh? But why would we use 30? Why won't we use something between 100 and 30? 30 is guaranteed. 50 is not. 75 is not. 62 is not. 300 is not. 30 is guaranteed. I mean, any situation we're going to run this transistor in, we're going to get 30. So when we calculate it, when we get a transistor and we use it as a saturated switch, we're going to use minimum beta. And then we don't worry about it, right? You understand? If I use 100, that means it might saturate down here in Alabama, but we get it up in Michigan in the wintertime, it's not going to saturate. If I use 30, it saturates in Alabama, it's going to saturate in Michigan, and it's going to saturate up on the North Pole because it is guaranteed, right? You understand that? So we use minimum beta. This also shows us our saturated voltage to emitter current. So this guy right here, collector to emitter, saturation voltage, look at this. Worst case is what? A maximum of 200 millivolts. Well, a maximum of 300 millivolts. So all we can say is that, so normally we assume if it's below 1 volt, it's what? It's saturated. Everybody understand that? So this guy, when I turn it wide open and it's conducting 200 milliamps, the maximum current, it's going to drop its maximum voltage. So this guy right here is going to be pretty dang close to zero. It's going to saturate real well. So this is what we need to calculate this thing. We need the minimum beta, right? You understand that? And we don't even, that's basically all we need. And make sure we don't exceed 40 volts when we turn it off. So if I'm gonna operate it in this saturation and cutoff, when I cut it off, it's going to have to block 40 volts. If I put over 40 volts on it, if I make it block over 40 volts, then it could do what? It could do damage. Okay, so what do y'all guys want to like? What do you want to turn on? So let's design a saturated switch. What do y'all want to turn on? So here's what we do. First of all, I calculate what we call we're going to call IC sat. So I've got this circuit right here. And what do we want to turn on? So let's just use a resistor up here right now. What size resistor y'all want to use? 13K? 10? We did 10K. 13K, but well, okay, 13K. What voltage do we want to, what voltage is required by that resistor? So this is one thing you're going to have to know is that once we move away from a resistor, most loads have a specified voltage. So what I do here is what voltage I use up here is what's required by the load. So what voltage do we want this load to run off of?
5 volts.
Okay, so we'll run it off 5 volts. Okay. So what we're going to do now is say, okay, what size, what would be the saturated collector current? How would I calculate the saturated collector current? So when I saturate the transistor acts like a closed switch. All of the voltage is going to be dropped across that 13K. So when that 13K resistor drops all of the voltage, the transistor saturates. And we're talking about all the voltage with this guy, right? You understand? Because here we're not even close. We're not even going to be close to saturate maximum current. So this said the maximum this transistor is going to drop is 200 millivolts. The maximum. So when we calculate that, what are we going to do? We're just going to use the applied voltage. So my IC sat is going to be VCC. So that's VCC divided by RC. That's how simple it is. That's my saturated current right there. That's it. Yeah, so IC sat would be equal to what? Is everybody okay? Now we're using a 2N 3904 to run this. This is well within its limits. Well within its limits. It can handle up to 200 milliamps. So what am I going to do next now? Well, I'm calculating the size of this resistor right here. And that's going to be connected right there. And I know this resistor is going to drop 4.3 volts, right? Okay, so what size resistor would I use over there? What beta are we going to use? We just got through, guys. This is 2N30, not what? 30. So I'm going to say IB sat, my saturated base current, is going to be equal to 385 micro divided by 30. What's that? 12.8. Sorry, guys. I keep unplugging my projector, my arm. Okay, so what size resistor would I go? So RB would be equal to 4.3 divided by 12.8 micro. I'm listening. I'm listening. What's that? 320. What's that? Not into, you're dividing it by. Yeah, we always go down with it. So it's just like the Zener. So Zener, we always round down. This guy right here, we always round. Except here, we're not as concerned with the tolerance. So what size did y'all come up with? What size did y'all come up with? Yeah, I knew 330 was wrong, guys. Yeah, we're dividing by the -6. So that's going to move the top number over 6, right? You understand that, at least. So what we got? I got 4.3, and this is something you need to see in your head. So if I've got a -6 on the bottom, then odds are my top one is going to move over 6, right? Y'all understand that? At least. So 4.3 divided by 12.8 micro times 10 to the -6, and that comes up and gives me 3,300, so we'd use a 330K. Well, somebody didn't say K. Somebody, huh? Well, if you had I know that's a legal excuse, Charles, but you were supposed to be doing the math. You're supposed to have calculated the 12.3 micro. So even though you shouldn't have seen mine, you should have been able to what? See yours, right? That's a good point. I know it might be hard to see. By the way, you see all these computers up here? So what do you, if you can't see from back there, what do you probably need to do? Move up. What's that? So it's 4.3 divided by 12.8 micro. Here's 12.8 micro where we calculated. Huh? So when you say 330, I think you mean 330 ohms, right? And I knew that had to be wrong. Why? Because we're dividing by micro. We're taking units and divided by micro, which means we're going to move it over at least six places, right? We could do this another way, by the way. And by the way, what's nice about saturated switches is we can do it like this. So I could come over here and have my transistor. Let's say I'm going to run a relay. We'll talk about this in a minute. And my relay is a 12 volt relay at 100 ohms. Okay, and then I'm going to come over here and run this through a transistor. And I'm going to put a diode right here, by the way. But I'm going to run this off a 5 volt circuit. And we'll show y'all that when we get back off breaks. So what I'm going to do, instead of doing that, I'm going to come in with a resistor like this. And I'm going to put either 5 volts or I'm going to put 0 volts right there. Would that work? Sure. So what's nice about a transistor is the current that I'm driving, or my power for my driver, does not have to be the power my driven does not have to be the power from the driver, right? You understand? Sure, we could do that. So I could say 12 volts, 100 ohms. I would calculate IC max. So I'd come up here and say IC SAT, would be equal to 12 divided by 100. What current would that be? $120 milliamps. So our 3904 would work great because it can handle up to 200. This is still half its capacity. So we'll never run it at 200, but we would probably run it up to 75% of its capacity. We don't want to run it wide open all the time, right? But that's well within its capacity. So this could be a 2N 3904. And of course, this guy here is going to drop 4.3 volts. So what size resistor would I use over there? Well, I would come over here and I'd say my base current, my saturated base current required to saturate it would be 120 milli divided by 30. $40? Yeah, it's going to be 40 milliamps, right? I'm sorry, 4 milliamps. I can't do math. And then I'd come over here and I'd say RB would be equal to 4.3 divided by 4 milli. So what size resistor would we use? Our calculated size would be what? We're going to ohms. No, we're taking a big number, 4.3, and we're dividing it by a fraction. Anytime you divide by a fraction, you're going to come up with a number that's bigger than what you start off with, right? You understand? And this is little things that y'all need to get a handle on so you can tell if your answer has to be wrong. Now, just because you get something greater than 0 don't mean it's right. But see, this is milli down here, so that means at least that top one, the decimal point's going to move over 3 times. What? 1K, close to 1K. 1K? So notice I had milli down here, and my answer, basically, I knew my answer was going to have move over what? 3 times, right? Y'all understand that? What do you mean? Oh, okay. And just punching the numbers in your calculator, and this is the problem a lot of people will do it, is they'll come up here and say 4.3, and then they'll divide it by 4. And we have this biggest problem with DC, where in DC they just drop the engineer notation. So what side? 1K. So now I could come over here and hook this up to something that provides 5 volts. Now it's going to be relative to the same common, but now I'm taking 5 volts and running a load that requires 12 volts. So your driving voltage does not have to be the same as your driven voltage does not have to be the same as your driver voltage, right? You understand that? But it takes a little bit of a different arrangement. But this would still be considered what we call base bias. Huh? Yeah, this is a switch. That's what we're doing. And so this is a neat little thing to know how to do, because now you can take a real small current and you could turn on things. So I could come up here and take a little tiny thing and turn on 100 LEDs, and we'll show you how to do that. We got a real neat circuit where it'll automatically change the voltage depending on what current's required. So you can take 1 LED and hook 2 in series, 3 in series, 4 in series. As long as you have the required current, the required voltage, you could hook as many LEDs in series, and every one of them it would give the same current, which is pretty. Okay, guys, you go ahead and take a break. So there's my relay coil. There's my counter EMF diode. It only comes into play when you turn the switch off. So remember that, guys. So if you ever have one that goes bad, then when you replace your transistor, you need to find that dang switch and find it. So we could go over there to the manufacturing line, and you'd see all the relays have a coil across it, so it don't wipe out my transistors in my PLC. You're okay on saturated switches. They're not hard to design. What beta are you going to, what do you do first? First of all, you see, okay, what load am I trying to run? What load am I trying to run? So you need to know what the current required, what the voltage in all you need to know on your load. And relays are usually measured in, the coils of relays are usually measured in volts and ohms, or they're registered in volts and amps. Voltage in amps is beautiful. Right off the bat, if it gives you the amount of amps, that tells you your saturated current you're trying to get with your transistor. And then you need to find a transistor that has what? That can saturate and handle that much current. I would probably give it a 50% safety zone. So if I needed 400 milliamps, then I would choose a relay that had a maximum current of 800 milliamps or 1 amp. And then you say, okay, what beta can I get? You look at the beta of the transistor. Remember, you have to use the what? The minimum beta. Minimum beta. So that's why. Why do we use the minimum beta? It's guaranteed. I know it's got to be at least 30. Now later on, when we get into amplifiers, if we use this transistor, we design the beta. We design what beta we want. Well, all we can do is we never can do better than 300, right? You understand that? But we design the beta we want. On a saturated switch, we're going to use the minimum beta because we're depending on the beta of the circuit. We don't have any more resistors in there that we can control that with. Very simple circuit to design. So you're using a very small current to control a big current, right? You understand that? So we run in saturated switches. Saturated switches in PLCs. So the outputs on DC PLCs are usually saturated transistors. So we have two on PLCs. Your DC outputs on your PLCs have two types of output. They're either transistor output or they're relay output. One or two. And if it's a transistor output, it's nothing but a what? Nothing but a saturated switch. That's all it is. Are you okay? Any questions? So saturated switches. What we'll look at next is we'll look at what time? We'll fix to let y'all go back to lab. We're gonna, I need to show y'all some of the things we're gonna have to do. So some of y'all are still working on your sensor lab. And Brandy didn't show up. Some of y'all hadn't finished y'all's rectifier lab yet, right? Which is really not good, right? Huh? Yeah. So if you're working on the sensor lab, you go ahead. I mean the solid state transducer lab. Go ahead and finish that up. If you have a little time, you need to drop back into your rectifier lab, and then the next lab we'll be doing is lab number. I don't have my lab book. It's the first one on bipolar junction transition, and then I'll have to show you all those stuff on how we're going to put that up because we can't use both power supplies on the train. We talked about that the other night, right? So your lab book, lab number. Number 33. So the next thing we'll look at is compensator amplifier, lab number 33, will be the next lab. Which is basically right after 32, and some of y'all are still working, right? Okay, guys, go ahead. And since I'm going to be here tomorrow, I can start uploading some of these lectures. Oh, no, y'all sit down a second. I'm sorry. There's one more thing I need to show y'all. One more. So what I did is I designed a little switch here. This is not a switch. I've got it operating in the active region. Because if we had a switch, we wouldn't. If we designed the switch, this right here would have absolutely no effect. So I'm using a 3904 transistor. So this is the little TO92 case, and but this could be a voltage regulator. So this is an NPN transistor, and on this one, if we look up the pin out, so we call it the pin out. The pin out shows you the assignments of the leads. So if we looked at the pin out for the 3904, it would tell us that the emitter is on the left. If we look at it from the front, so it's got a flat side to it. If I can get it up here, you know, see it. So it's in the shape of a D. So if we look at it from the flat side, the emitter is on the left, the base is in the center, and then the collector is on the right. So I designed a little circuit. Wasn't very hard. And I'll tell you what I ended up with. Is I didn't want to run it in the, I'm not running a saturated switch or a switch. I'm running it in the active region. So I've got my transistor. I'm using base bias. And then I've got my 2N3904, 04 rich. And then in my collector, I'm using a 330 ohm resistor. And then on my base, I've got 100K in more. And I'm going to use use, I think, 15 volts for the power supply. And we're not going to calculate it. So this guy's going to be in the active region. I'll show you how we know that, of course. How do we know it's in the active region? Y'all tell me. I'm listening. But what do we measure? Well, we measure VCE. I'm not going to measure it. But if voltage collector to emitter measures less than a volt, we say it's saturated. If it measures VCC, we say it's cut off. If it's between 1 volt and VCC, we say it's in active. So what I have here, guys, is I'm going to look across my collector resistor, because my collector resistor and my transistor are in series with each other. And I've got this sitting at I got it setting at nothing because I don't have my power supply. And let me put my camera back over there. So the power supply, I'm going to turn it off while I hook it up. Here's my positive voltage. I'll hook it up to the collector and the base. Here's my emitter. Here's my negative voltage. I have it hooked up to the emitter. And let's turn it on and see what happens. So my collector is measuring around 3 volts. That's my collector resistor. So that means I got it set on 15 volts. So I'm dropping 3 volts across my collector emitter, my collector junction is focused in my collector resistor. So that means my transistor is dropping around 12 volts. I'm going to get it to focus in. Come on, focus in, please. This camera's usually pretty good at it. There we go. So what I'm going to do is I'm going to come up here and take this guy right here. I don't know if I can get both of them up there at the same time. And what I'm going to do is I'm going to take my soldering iron and I'm going to bring it up close to my transistor. What should we expect to see? What do you think happens to the beta when we heat the transistor up? Is the beta going to stay the same? Huh? What would you think it would do? Would it go up or go down? Yes, you had a 50-50 chance. Beta's going to go up. Because if we heat these things up, their resistance goes down. We saw that with a regular diode, right? You understand? We hooked it up over there. We reverse biased it. I heated the diode up. The leakage current went up. And the leakage current went down. Well, if your collector current goes up and we don't change our base current, then that means the beta has to be going up. And this is why beta is in such a big range. So I'm going to try to get this over here without burning up everything. I think about this. I got to show you that video. I'll put it on one Brian showed me the other day, where this guy's talking about a soldering iron, and he says you can. And guess what he did? He put the soldering iron and put it right there. And he said something stupid about, you can feel it while it warms up, but it was already hot. And then he dropped it. Where do you think he dropped it at? In his lap. So if the voltage drop across the resistor is going up, what does that mean the voltage drop across the transistor thing? Okay, guys. I got two things. I got this, And then I got my transistor. We're not going to draw the other part of the circuit. So if I was to come up here and redraw this as its equivalent, I would come over here and do this. We're operating in the active region, right? Kirchhoff's voltage law says the sums of the voltage drops have to equal to the applied voltage. I'm measuring the voltage drop across here. So let's say this is 5, and we have 10 volts applied. If this is 5, then this guy here's got to be 5. Right? You understand? If this right here goes to 7, what's it across the rheostat's got to go to? Huh? It's got to go to 3. So I'm measuring across this. So if I see the voltage drop across my resistor going up, it means the voltage drop across the transistor has to be doing what? Going down. Okay? You understand that? Okay. So when I heat this thing up with my iron, what would cause the transistors to go up? Well, that means that means the collector current has to be going up. But the base current is not changing. The base current is set with that dang resistor over there on the left hand side. So if the base current is going up, it means the beta of the transistor has to be changing. Right? You understand that? So I'm going to come over here and start heating this thing up. And notice the voltage drop across my resistor is going up. So what does that mean? The voltage drop across the transistor is doing what? Going down. I'm not touching my transistor. I hope I'm not touching it. I got a lot of rubber wires up here. All I'm doing is bringing this close to it. Now eventually we could drive this thing into saturation. And then when I take it off, eventually it would start going down. If I hit this with freeze spray, all of a sudden the beta would go way down, right? You understand? And the transistor would drop more voltage. So what can we, from this little demonstration, what can we come up with according to beta? So what happens with beta when temperature goes up? What happens to beta when temperature goes up? It goes up. What happens when beta when temperature goes down? It goes down. So I've got my car stereo out there, and we don't want the beta to change on our transistor, because that means I got out there in the summertime, my amplifiers would saturate, my thing would be, and then in the wintertime I wouldn't hear hardly any volume at all. So what we're going to look at next is how do we control this? How do we keep the beta of the transistor from changing? So we have different ways we can bias that transistor. Base bias is but base bias in a saturated switch means nothing, because we use minimum beta anyway. So if my beta goes up, you can't saturate it more than it's saturated, right? You understand? So once that collector resistor drops, once that collector load drops all the voltage, collector current can't change. So base current can go up, right? Or base current can change. Anything can change. Beta can go up. So beta goes up to 50. Well, I saturated it at what? 30. So if we saturated switches, if they're designed correctly, you don't worry about temperature. You have no problem. In an amplifier, though, you're running that sucker in the active region. So it's not acting like a switch anymore. That sucker's acting like a rheostat. But the rheostat is changing with temperature. So that would be awful, right, in an amplifier circuit. So we'll show y'all, next thing we're going to get into is the way we can bias, or we call it voltage divider bias, where that thing is going to be steady no matter what temperature you're running at. So we can bias it in a way where temperature won't affect it. And that's what I'm trying to get to. So beta changes with what? Temperature. If beta changes and I don't do something, then my collector current's going to change. But saturated switches, we don't worry about it, because why? Because we use minimum beta. We saturate it at minimum beta. So if beta goes to 100, collector current can't change, because that resistor's already dropping all the voltage anyway, right? Okay? All right, y'all go to the lab now. So this is bass bias. Bass bias is, we wouldn't use bass bias as an audio amplifier.